information after this class, please mention me, maybe email or through the Moodle system. Okay, once you have more information about other schedules. Okay. So probably if not Friday 15 this time, okay, because you don't have TA, right? So I believe this should be okay. This 3:20. Okay. Or if not, then Saturday. Okay, maybe other suggestions or maybe having certain requests based on your schedule time. Okay, I think if not Friday, Saturday, 3:20 or 16. Okay, Saturday, I believe all time okay, right? From morning to afternoon, around that. Okay. Okay. Now it's the chapter 7. Still the chapter 7. Now this is the improper integral. But let me write some notes for you for the improper. Okay. Why it's called improper? That's the first thing. Okay. So proper, I believe you understand proper. Okay. Basically, proper means as it is, as regular as it is. Okay. Just integral. Okay. Proper integral. But this is improper integral. So there will be something that makes the integrations different from the proper one. Okay. For example, okay, I will divide this improper becomes 2. If you have definite integral, with infinite, okay, infinite interval. For example, you have integrations fx dx, and maybe from 0 or maybe from some constant a to infinite number. So that's what improper means. Okay, so the first is the definition is having infinity, okay, approaching infinity for the integrations, and the second, this is one, and the second, the functions has discontinuity. In the, let's say, interval a, b. Let's say that you have a, b, fx dx, and then you have c in between a and b. And then fc is, let's say fc is undefined. But in this section, okay, because of these two cases, the infinite interval and the discontinuity, we need to approach the integration with some methods. Okay, but let's take a look at the graph. Okay, so if you see y equal 1 over x squared, okay, so it's going down the blue color line, the curve. And if you see the area under the curve from 1 to some number t, okay, let's just evaluate this area as at. So let's write at as integrations of 1 to t from the 1 over x squared dx. And we can integrate this easily. We can write the 1 over x minus, okay, and then plug in the 1 and t. And we can write this 1 minus 1 over t. Okay. If you see the um, the expression 1 over t, okay, if you see the area at, the maximum possible area is 1, right? Because if you add like t, you have minus 1 over t, right? So for example, if you have 1 until 2, it's become half, and it's become only half, right? If you have like maybe 10, it will be 9 over 10, right? So the maximum possible number for area is 1, right? The maximum. Or if you consider some t, maybe 1.1, really close to 1. So the answer is almost 1, at least, okay? At least the maximum possible answers. So we can write here, okay, is always less than 1, okay? No matter how large t is. Okay? And we can write as a limit, okay, as t going to infinity, okay, of the area, we can write this as 1 minus 1 over t, and then it's only 1. Because 1 over t, when you approach limit to infinity, it becomes 0, right? So we can write 1 infinity. If we have this kind of problem, we can write adding the limit and then write down the functions. And after some calculation, we can conclude that this is 1. And we are conclude the solution for the 1 over x squared from 1 to infinity is converge at 1. Converge. So we say that this is convergent. Okay, this is just example from uh, some simple functions that we can um, we can review easily, very easy. That this should be converged at one. Okay, so basically the idea is uh, we need to involve uh, the limit, okay, the limit, and we need to make the limit approaching infinity and changing the end point in the integrations with some variables, okay, so that we can compute this, okay. If we are just computing the 1 to t, it's okay, right? But if we are computing like directly 1 to infinity, it's difficult because infinity is really abstract, right? It's not an exact number, right? So we need to rewrite this into this limit as t approaching infinity, and we solve this first. And after we get solution from here, we are compute the limit. If the limit have number, we say it's convergent. If having stay infinity, then we say divergent. Okay, I will explain later. Okay, so maybe the definition. Let's say this is the type one, the infinite interval. And let's say A is let's say if integrations from A to t of fx dx exists for every number t greater than a, then and provided that this limit exists. Okay, this is A. Also provided that this limit exists. So now, okay, because we are involving limit, okay, because of this limit as t approaching positive infinity or negative infinity, all the method in your chapter 2 limit is applicable here. And also the L'Hopital rule also applicable. So at least two process, okay? So first, the first process is to integrate the functions first, okay? Integrate this first. And after that, compute the limit, okay? So at least two process, okay? The integral and the limit, okay? Okay, so yeah, it's two positive infinity and negative infinity. But also, okay, you can combine A and B. You will have negative infinity and positive infinity. What you can do, you can separate become two. Find a number that you feel that the number will be nice to be calculated. For example, maybe 0 or 1. So you can write negative infinity, like for example, okay. So if you write the like this one, okay, you can separate this become maybe just let me write just a constant plus a and infinity and then fx dx. Okay, and a can be any number. Okay, it can be any number. Okay, and also you need to consider what kind of functions you are evaluating. Okay, so you can separate them, and you need to evaluate each of these integrations. Okay, this negative infinity and the positive infinity. So you need to write the limit approaching this negative and limit approaching this infinity. Okay. So basically, you can combine both of these cases. And also, when you are having your results, your calculations, improper integral. Let's say the first one is a, and b. They will have like convergent or divergent. Convergent if limit exists, and divergent if limit doesn't exist. Okay, for example, if you are evaluating both of these cases, okay, maybe this is okay, I get maybe some finite number here for this part, okay, but this part you get maybe infinity. Your conclusion is divergent. Okay, so whenever you find, if you like separating these functions and then one of them diverge, then you can just conclude diverge if the question is only asking whether it's converge or diverge. So usually the questions will ask like You will be given the integrations, and you need to conclude whether it's converge or diverge. But if both have number, then you need to compute the number, and you need to state the number. Okay. Then I think I can write the third case. So if both okay, let's say this is convergent, then we define where A is any real number. Okay. Okay. Now we have the first definition. Okay. Any questions? Any questions? You need to write all this. Okay. 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 Let me give you the other illustrations. Okay. Other illustrations. Let's say we have integral from 1 to infinity, um, 1 over x. Before we have 1 over x squared. Now we have 1 over x. Now, because we already have definitions, we can use limit, okay, to compute this. So first, we can add the limit. Let's say t. Actually, you can use any variables, okay, like t, u, anything aside from the x. Okay? But usually t. So 1 and t, and then this is 1 over x dx. Okay. So 1 over x, if you integrate, it becomes ln, right? Ln, right? So I can write this limit t, and then the result is the ln x. Okay. And let me put the number here. Still, we have limit, and then Let's write ln(t) minus ln1. So what will happen now? It will be diverged, right? Or we can say this is divergence, or the function is divergent. Okay, interesting, right? When we are using the 1 over x squared, okay, remember, I will write in the left here, if we have this is 1, right? Converge. And this is diverge. Okay. If you see the graph, the 1 over x squared graph is really getting closer to 0. Okay. And if you compare to 1 over x, it's like it's still having, yeah, maybe it's not to scale enough, but I believe the 1 over x will have a large gap here, in which if you are, imagine when this is going to 0, this is still having a quite number, okay? A few number. And if you are going to infinity, still we can say that 1 over x is still diverged. It's not going to finite number. Okay. It's almost like, do you remember the sequence and series, a geometric series sequence? Like you have the ratio, and you can plus until uh, infinity. Like for example, okay. For example, you have uh, 1 plus half plus 4 plus 8 plus and maybe infinity, like that. This is the same case that can happen. And if you plus this, it will be 1. It's almost roughly 1 plus 1. Okay, 1 plus 1. If you remember, it's, I think it's high school, right? So basically, it's similar. And in calculus 2 next semester, we will go deeper into the sequence and series. And the purpose is the same, finding the convergences. Okay, which one is converged, which one is diverged. So this is I think like an introduction for the convergences. So we can state that the 1 over x is infinity or diverge, and 1 over x squared is converged. And we can actually make some relations. So if we have integration from 1 to infinity, 1 over x with power of p. Okay, we can say that, or we can find, or let me write the question. For what values is integral become convergent? So we can make a new relations, okay, and to find this p. Okay, before I will show you that 1 over x and 1 over x squared resulting the different results, right? So we can write, or maybe writing here. Let me make this become limit as t going to infinity, and then making 1 t and then 1 over x. Okay, and then we have limit as t approaching infinity. Let me write a step-by-step process. And then dx. And then p is any real number p. Okay. So I can write this x 1 minus p. Okay. So just plus 1 and over 1 minus p. Okay. From 1 to t. Now I can write this factorize the constant. The constant is 1 over 1 minus p. And then plug in t and 1. So if you plug in t here, imagine this will be 1 t 1 minus p, and then I can write this as 1 over t p minus 1 and then minus 1. Because 1, no matter what real number you are having, it will still be 1. Okay. Now let's see these terms. Okay, let's see these terms. So we need to look at this p, okay, and look at this t approaching infinity. Okay. So if p greater than 1, so p minus 1 is greater than 0. So if p minus 1 is greater than 0, imagine here, imagine this become greater than 0. Okay. What will happen with the infinity? So infinity, 1 over infinity is 0, right? So if p is maybe 2, 3, greater than 1, so it will be 0, right? Oh, wait. I think someone connecting with me. Maybe with in different classroom. Wait. Okay. It's a little bit funny. Yeah, you can take some break if you want. Yeah, I'm not sure why. Yes.
Would the 1 be the -1? Because it was -1 over x. Both of them minus.
Yeah, you can plug in t. So one minus 1 over t minus minus. Right. Minus positive, right? Right.
Okay.
Okay. And then positive, I'm just switching one and negative one.
So you put minus, or you put minus t instead of x.
Yeah.
Or
Yeah. Mhm.
so yeah, 16.
What,
Motorcycle license test.
what time? What time?
16 morning.
Morning.
So if you will test 16, can you tell me before it is close to 16?
Okay.
Then I can change my time.
Okay.
Can I see a previous?
Which one? This one?
This one, why smaller, be smaller, t,
Because
b, the t to b, t will be smaller.
yeah. Hey, wait. Oh yeah, right. This is B. Sorry. Okay. So I think I've made mistake. This one should be greater. Should be greater. Right. Okay. Should be greater. B should be greater than T. Okay. Okay. Sorry. But at least the formula is correct. Okay. Sorry. Yeah, I'm switching this too. Okay. Maybe any questions first? Okay. And then this part. Okay. Let's continue this part. So as t going to infinity, if you have p minus 1, this all will be going to infinity, right? And if you have 1 over p minus 1, this is going to be 0, right? So this is the conclusion. So, okay, because of that, so if you have integrations dx, this will be 1 over p minus 1 if t is greater than 1. So the conclusions we can write, this is converge. So when you have 1 over x and then some real number greater than 1, you can just compute 1 over p minus 1. So if you have like 2, it's 2, then 1. If you have 3, it's 3, then it's 1 over 2. It's 4, then 1 over 3. Okay? So that's the first p greater than 1. And for p equal 1, we already did with the 1 over x. Okay, so let me just write if p less than 1. Okay. So if p less than 1. So p minus 1 is less than 0. So if we have 1 over t and then p minus 1, we can make it t 1 minus p, right? And we can write that as t reaching the infinity, t 1 minus p also reaching the infinity. So we can say that this is diverge. So conclusion, this will be convergent if p is greater than 1. This is divergent if p less equal 1. Okay, let me give you an example for the first case, the first definition. Example. So integrations e to infinity 1 over x and ln x cube. Yeah. And let me give you two questions. So the second one will be the I think it's not too difficult, right? But basically, okay, with all uh, the techniques of integration that you have learned before, you will need most of the techniques, okay, to solve this, especially the substitutions, the integration by parts, okay? And you can solve before you are inputting the number. You can solve the integration first if you want to be more like really step by step, really clean. Okay, if you are mixing all together, maybe you will be confused. Okay, so you can solve the integration first, and then later you can put in the endpoint, okay, and use limit to compute, okay, as at the end. So we can write this as limit st from from e to t, and then 1. And you see, this is the substitutions problem, right? You can use this substitution. So you can have u is ln x, and by doing so, you can cancel the 1 over x in the equation. And then you need to change the integrands. So from e to t becomes 1 to ln t. And then this will be 1 over u cubed du. And 1 over u cubed, it will become squared, 1 negative, and then 2 u squared. And then plug in the ln t and 1. So negative 2 ln t squared, and then minus or plus half. This becomes 0, right? So we can have the solution is half. And we can say that the integral is convergent. Okay, any questions? Okay. The other example, I think it's also substitutions. Okay, also substitutions. So I can write this limit. This is 0. This is t. Let me write in here that u is 1 plus x cubed, and then du is 3x squared dx. Right. Okay. Let me just write 1 over 3, and this should be u integral of du. If I'm substituting the u, it will be 1 until 1 plus t cubed. Let me just integrate the u. This will be half and then 2, right? Okay, so I will convert back to x without any mentioning the integrals on u. So limit t. So 2/3 1 plus x cubed from 0 to t. So I'm skipping some process. Okay, so I hope you don't mind. So I will get the result is 2/3 and then 1 plus t cubed minus 1, right? And this becomes still infinity, right? So I can conclude this is infinity, and we can write this is divergent. Okay, let me move on to definition type 2. Okay. If you have the discontinuity. Okay. So if functions is continue, um, or let me write with different color. On A to B, but not including B. Okay. And discontinue at B. Then we can write limit st approaching from B to the left. From the left, okay, sorry. And then write A, and then D, and then fx dx. So if this limit exists, okay, and then secondly, if functions is continuous, or whatever continuous, continue on AB, not including A, okay, and discontinue at A, then can use the limit as t approaching A from the right. And this is true if this limit exists. And we can say the integral of A b fx dx convergent or divergent. Convergent if limit exists, and divergent if limit doesn't exist. And also we can have the third case, if we combine A and B, okay, we can combine A and B. So the other one will be C if functions has discontinuity at C, and then the C is between A and B, and the integral AC and integral CB both are convergent, then we can separate it. So we can compute the integrations on separate integrals. Okay. So if you have C, okay, so C is discontinuous. Okay. C is having discontinuity. So we can separate this AB, become A to C and C to B, and we can compute each one. If you have the finite answer, if you have the number here, then it is a convergent. Okay. But if not, then maybe one of them is diverged, then it will be divergent. Okay. Okay, any questions? Any questions? Okay. Let me give you another example. Okay. Let me just write into new page. Okay. Evaluate the integrals. I'm giving you several minutes. If you finish, raise your hand. Okay. I want to know whether you can finish this or not. We are confusing the number here. Before you going to number, maybe you can integral this first. Okay. Find the result from this, and then observe the number. Okay. Mm. How? Huh? Hmm. But you can do this if we need to integrate first. Okay. 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 You get it? So, so. Yeah, yeah. But do you have any idea how? Okay, 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 okay. Hmm. Yeah, yeah, yeah. Mm-hmm. Hmm. Anyway, like I said, maybe in the previous, or maybe in the early class on integral, that uh, mostly integral will be more difficult than the derivative, okay? Because we need uh, to think backwards, to think how to reverse the functions, right? You know, the derivative is much more easier because you need just to derive, right? And uh, like derivative is come from, like you have the maybe this parabola here. Okay. Derivative is basically every point in this parabola you can make it like a tangent, right? And you can see, okay, the tangent is just a line, okay, and this is parabola. So basically finding the tangent is pretty much easier. But if you have a tangent and you need to imagine how it looks like before, then it will be more difficult. So basically, integral is more difficult. And you know that in the MIT, every year there will be uh, like a competitions, like how to say that, like, yeah, it is called the B, right? The MIT integral. I think some of the competitions, one or two students, they record. I've saw like one or two videos, like uh, they will hold the competition for the students, so any students can join the competition, and they will have like a tournament. So like a tournament. So maybe the student and versus the student, and then they compete, and who will win, they will get to the next round until the final. Okay? And how they compete is there will be like a referee, the judges, and they will be given the question. It's like, for example, like this question. Okay, this is not from MIT, but for example, they give these questions, and the student in the front, they need to think the solutions. Like they do not need to like writing all the process in a clean way like you did in the exam. They don't need to, but they just need to write the simple like the answers. Okay, maybe the answer is pi, or maybe pi over 4 plus blah blah blah. They need to just writing the answer, and if they write as soon as possible, then they will win the round. Okay, so okay, I'm writing this. Okay, and then the student win. Okay, if both students they cannot solve, the judges will give another questions, and they will doing the calculations. And if you see the maybe you can googling like B MIT integral, and maybe you will see some questions. If you did that and maybe you can solve that, you are really good. Because I've seen like some integrals, maybe I can do like 2 or 3, but most of them I need to think first. Okay, this is really difficult, and you know the there are audience like they just it's not just like the two students like writing the answer, but the the viewers, the audience, they also like cheering. Yeah, yeah. It's like a bunch of nerds cheering. And then some of the students they use some software from laptop and checking the answer. Oh, here, and then writing the writing in the paper. So yeah, like a bunch of nerds. But you can check if you want. Okay? I think it's called the BMIT integral. And I've got several suggestions, like several idea uh, for solutions. Maybe later I will show you some parts of what kind of idea. So it's not about like how to solve the integrals with like, okay, we need to use trigonometric integrals. No. It's like it's more complicated than that. Okay, now back to this question. Anyone solve? Anyone solve? You solve? No? Why? Why? I saw your equation. I think it's already good. But why? Why? Why you give up? Give up? No. Hmm? Um, almost, I think. Some part is true, but yeah. You need to check. Get it? Yeah. You can continue. You get it? Yeah. This. You have 1 over t, right? Change 1 over t into other variables, and t will be infinity, right? You get it? No? Oh, limit. Okay. Okay. First of all, you see the 1 over x. Okay. I think this 1 over x is quite quite a trouble, right? So what I did is let me uh, write down this u as 1 over x first, okay, and change all to u. So I can write this, or maybe I will add the limit first. Okay. So the limit is, if you see -1 and 0, and you think any number maybe in between, I think the possible one that makes this function discontinuous is 0, right? If you plug in 0 here, is diverge, right? So 0, I will exchange to t, okay? And then t will approaching 0 from the left, right? And then this is -1. Let me write all terms. And then let me write this 1 over x, and then e1 over x, and then 1 over x squared dx. Okay. And if I'm writing the u, and then du is -1 over x squared dx, then I can exchange this, and I will get the limit as t approaching 0 from the left is negative. It's u e u du, and then changing all the -1 to 1 over t, right? Okay, now we need to solve these integrations. So let me just write this u1 0 so I will get the limit t and the negative of u eu minus eu, and this will be computed from -1 to 1 over t. I think you get until at least this result, right? And then writing limit and then let me change this to EU, or let me just change the integrals. Let me just change this, and then this will be from, yeah, just change, just flip the integrals, okay, and the negative will be cancelled, okay, and now let's maybe make red. So negative 2 e -1, right? If we plug in here, it's -1, right? Okay. And the other is 1 over t. So one over t, e 1 over t, and then minus e 1 over t. Or let me just write in simple way, 1 over t minus 1, and then e 1 over t. Okay. Okay, now we need to observe this 1 over t, 1 over t. Okay. Imagine 1 over t as s. Okay. So as t approaching 0 from the left, what will happen to the s? Imagine 1 over immediate functions 1 over x. What will happen? Minus infinity, okay? Right? Now we can change this limit and becoming limit as approaching negative infinity. And we'll write this 2 over e minus this s minus 1 and then e s. And let me write this. We'll write negative 2 over e and then limit negative and then limit as negative infinity and then s minus 1. Or let me write, maybe I will write like this. Okay. So s minus 1 and then e with negative s. And what will you do? Huh? What you will do? Yeah, it's 0. But you can see that you can solve this. It's L'Hopital rule, right? Okay. This is indeterminate forms, right? So you can use L'Hopital rule. So negative 2e minus this will be 1 and then negative e negative x. And this you can write negative e s and negative this. Okay, 0. Okay, so the solution is negative 2 over e and it's convergent. Okay. Okay, so my suggestions for your final exam, it's from chapter 5 to 8, but because integrals will be included also with derivative and limit, then you need to understand all chapters actually. Okay, at least the necessary points. Okay, like L'Hopital's rule. Okay, and the derivative maximum minimum value, but not necessarily like just the derivative, but in integrals. Okay, derivative in integrals. Okay, especially in the improper integral, you need to remember the limit. Okay, remember limit. Okay, any questions? Any questions? If not, then I think finish for today. And if you have more information about your schedule, okay, please inform me. Okay, inform me as soon as possible. Okay. Which one?
This one.
Mhm.
I change it into
Yeah, same, the same.
and why you can write this don't have to change.
because I'm changing back to 0 and t, and changing back u into x.
Oh.
Okay, but this is should be the same result. Okay. Because you cannot add ln. If you add ln, it will be different function. You can like for example, you can add ln, but the result, maybe if you write this, right? This is y, and you add ln, yeah, ln, right? But still, you cannot add the bottom one, right? Yeah, that's why it's wrong. So the result will be it's ln, but not the y, right?